Okay, we're going to begin Chapter 9. So Section 1 on Chapter 9 deals with quadratic functions. They're basically a quadratic polynomial, normally a trinomial, but we also have binomials and single term also. So let's just take a look. Oh, there we go. Try that. Let's just take a look at an example of a quadratic function. Y equals negative 1/2 x squared plus 3. It needs to be in the form of ax squared plus bx plus c, where b and c can both be 0, but a must exist for it to be a quadratic. Okay? The graph of quadratic functions are what we call a parabola. Okay, it's like a skinny U shape. They can either face downward or upward, and it all depends on your a value. If a is greater than 0, it faces up. If it's less than 0, it faces down. Okay, you can create a table of values to graph. We've done that before. You need a minimum of 5 values. And the other thing we're going to talk about today is your domain and range. We've talked about all of these things before. We're just putting them all together. So the domain is your x values or input, and the range is your y values or your output. Okay. Also, what we're also going to talk about, domain for most parabolas will be all real numbers, or quadratic functions will be all real numbers, unless we've put a parameter to limit that. So let's answer a couple questions about this. Number 1, identify the values a, b, and c in the quadratic function. I'm just going to write in a, b, and c right above those coefficients so that I can say a is equal to 3. B is equal to, the sign in front of the coefficient goes with it, negative 5. And c is equal to 2. Easy as that. Does the graph of 3x squared minus 5x plus 2 open upward or downward? And all we care about here is that a value. Since a is greater than 0, it opens upward. Okay, that means it has the basic shape like this. And number 3, identify the domain and range for the function who opens upward with a vertex of 0, 5. So let's go up here, and I'm just going to kind of steal and use this graph. Here's my vertex at 0, negative 5, and it opens up, and at this point I don't really care how skinny or how wide it is. I just care that it opens up to kind of get the general shape, so that I can say the domain for x is all real numbers, just because it almost always will be for quadratic functions at this point. My range is the pickier or trickier thing. Up here, if I look at this example, it says y is less than or equal to 3. So it went from its vertex and it said all y values that are less than that because it's opening down. So here I'm going to say y is going to be, since it's opening up, greater than or equal to whatever that vertex point is. And in this case, it's negative 5. Okay, so let's go ahead and do a graph of one of these. So it says create a table of values. I've already inputted the x values for you, so we just have to find the y values. In order to find those y values, we take our x value and plug it into our function right there to see what it should be equal to. So 2 times x squared. So 2 times negative 2 squared is 4, times 2 is 8. 2 times negative 1 squared, 1 times 2 is 2. 2 times 0 squared, 2 times 0, sorry, 0. 2 times 1 squared, 2 times 1 is 2. And 2 times 2 squared, 2 times 4 is 8. Okay, so we've got our table of values. Let's just plot those on quickly. Negative 2, 8. Negative 1, 2. 0, 0, 1, 2, and 2, 8. And you can kind of see, I picked values that they kind of mirror each other. And you can kind of see on here how those values go together. And then, because we know this is a U, we're going to connect those points kind of a sweeping motion. We're not just going to do straight lines. The vertex you can either get right here from the graph, or from the table, or from the graph. So the bottommost or topmost point, okay, where things kind of mirror off of it, is 0, 0. I can tell from the graph because these points mirror off of it, or from the table, I'm sorry, or from the graph because of where the bottom point. Does it open upward or downward? That's kind of a silly question at this point. We already see that it opens upward because A is greater than 0. Because my A value is 2. B is 0, C is 0 in this case. But it's still a quadratic function because I have an A value. All right. Identifying quadratic functions from a table. Okay, I'm just going to do one of these examples with you. Your book has another really good example in it. 3 steps. Step 1, check for a constant change in x. So this says calculate the second value minus the first value. So these arrows are kind of backwards because I should do -1 minus -2, which is -1 plus 2, which is 1. Another way to think of it, and this is probably why they drew the arrows this way, is how much must you move to go from -2 to -1? Up 1. So then I always put a plus or a minus there. To go from -1 to 0, I have to move up 1. From 0 to 1, I have to go up 1. And from 1 to 2, I have to go up 1. Okay? So that's good. My x's have to be a constant change. If they're not, then I can right away say it's not a quadratic function. Okay, so now the y values, there's going to be 2 steps. The first step is to find the difference of the y values. If they are constant, the function is linear. Watch out. Step number 2 over here when you guys do that. Step 3, it says find the second difference in y values. And if the second difference is constant, then the function is quadratic. And that's the key here. You have to go to the second difference of y values. So, to go from 12 to 4, I'm going down 8. To go to 4 to 0, I'm going down 4. To go from 0 to 6, I'm going up 6. And to go from 6 to 28, I'm going up 22. Don't panic yet because I don't really care about the first difference in y values. I know it's not linear because they weren't all the same. So now let's check the second difference. To go from -8 to -4, I have to go up 4. To go from -4 to 6, I have to go up 10. I don't really have to check this second one, but I have to go up 16. Because these are not the same value, for instance, like -3, -3, -3, or something, this is not quadratic. Okay? Oh, let's hope I can finish the video. Okay, last one. I think we can finish it. Because this is just really quickly how to find that domain and range. Okay, and we're just going to talk about flattening our parabolas into kind of a straight line because then it's easier to tell. So the domain, you're just going to take your parabola and flatten it out and squish it down to this x-axis. And like I've said before, for quadratic functions, your domain will almost always be all real numbers. Okay. For the range, it's a little bit trickier, not too bad. You're going to take it and you're going to squish it over to the y-axis. So here we have it right here. It's squished over and this extends up right here. And there it is. Your range is always going to be y greater than or less than whatever the vertex is. So if it opens up, it's always going to be y greater than or equal to the vertex. If it opens down, it's always going to be y is less than or equal to whatever that vertex is. So let's just do one of these down below. Domain. Oh, guess what? All real numbers. If I squished that down along your x-axis, it would hit all of them. Because remember, these things go on forever. My range, y, is it going to be greater than or less than? It opens up, it's going to be greater than or equal to. And my vertex down here, if I squished it over, 0. Okay, so hint over here, this is going to be y less than or equal to. Okay, you guys just need to finish that domain and range. You're done with 9.1.